So today I will first tell you what is discrete uniformization theory. And I will introduce the second discretization mechanism. So I will also tell you the associated variational principle. So let me quickly recall what we did last time. So here S is a connected surface. This is the surface. And in this setting, we impose no condition on the surface, only connected. So the surface could have infinite topological type. It may well be the torus with a Cantor set. So this is a really general series. It's like uniformization theory with no constraint of topology. So this is a topologically calculated surface. And V, the vertex set is always as a singularity. And we define the PL metric. V on this triangulated surface. Because we have a triangulation, so we can now just specify the length of the edges. Is essentially the same as a length function. You assign every edge a positive number subject to the triangular inequality. Those Li, Lj, Lk are three numbers assigned to the edges of a triangle in the triangulation. We want the inequality. Reconstructed the flat cone metric by making every triangle. A very special class of circle packing metric, which Thurston studied. The circle packing metric is a way to assign every vertex a positive number. From this radius assignment, we produce the edge length. So the length at two vertices, Vi, Vj, is sum of the radii at the two vertices. So here, in other words, we're going to make this triangle to be the triangle coming from tangent circles. Oh, yes. Yes, sorry. This is right? Oh, okay. Okay, so by elementary geometry, we can, so every triangle can be constructed in this way. And we can even figure out what are these three points. It's nothing but the tangent point of the three inscribed circles. And so I give you this triangle, you draw the inscribed circles, and you measure these distances, and this will be the radius. Okay, so every single triangle comes from this picture. And we're going to use this picture to do some computations later on. And also for every PL metric, we have the discrete curvature of this metric. I'm going to use abuse the user notation. There is a metric, and also now represented in terms of the edge length. And in case of circle packing, I'm also going to use just the radii to indicate the curvature. The curvature is concentrated at the vertices, and they send the vertex to 2 pi minus the cone angles. In case we have a triangulation, this curvature is independent of the choice of triangulations. With the triangulation, we can compute it by counting, take a vertex and look at all triangles adjacent to this vertex and count those angles. So this notation stands for angles in the triangulation with vertex V. So that's the cone angle, that's the curvature. So yesterday I was a little bit quick in proving it, but I think I'm gonna skip the details of it. But here is the first theorem. This is really beautiful rigidity theorem proved by Thurston, saying, which says that if I have two circle packing metrics on a closed, the surface has to be a closed triangulated surface with the same curvature, such that they have the same curvature, these two as a function from the vertices to R. So it's a point-wise the same. And then these two polyhedral metrics differ by a global scaling. And that's a necessary condition. So this implies R equals lambda, R tutor for some lambda positive. And the proof, I was quick yesterday, but I think I'm going to skip the details. But the key to the proof is this observation by Thurston. It's very highly geometrical and pictorial. So suppose I have a Euclidean triangle constructed out of three pairwise tangent circles. So let's call this the radius 2, radius 3, and radius 1. Okay. Now let's fix, and it has three angles, and let's call this, say, angle theta 1, theta 2. And now let's fix the radii to R3. I'm going to increase the radius of R1. So let's make R1 bigger, and let's try to observe what happened to the angle, because according to the curvature formula, the metric in the discrete settings are edge lengths, and the curvature are more or less the angles. And so this is really a study of the discrete relation between discrete curvature and discrete metric. And so if we increase the size of it and keep tangent, and then the center of the triangle moved, and the triangle becomes something like this. And so what Thurston observed is that if we do that, this angle is going to be decreasing, the angle at the vertex 1, and the angle at these two is going to be increasing. Okay. It's going to be increasing. So, and just based on this very simple observation, and one can give a proof of this. I'm going to make this picture will be so in Thurston's formula is that a partial R1 is going to be negative, and partial theta 1 partial R2 is going to be positive. Okay, so we're going to quantify this today, and there is really a very beautiful variation of principle coming out of it. And so this is really, I'm going to give a second proof of this today using variational principle. Okay, so this is the rigidity theorem. And now let me talk about what is the discrete uniformization in this setting. Yes, that's a great observation. So this is a very special class of polyhedral metric, especially if you look at the boundary of the tetrahedra. This is a triangulated two-sphere. The space of all PL metric is 6-dimensional because it has 6 edges. You can assign a 6 positive number subject to this open condition, and so it's a 6-dimensional. In fact, a convex polytope. And the space of all circle packing metric on this tetrahedra is only 4-dimensional because you can only assign 4 numbers there. So it's a special class of it. But in Thurston's mind, if we fix this triangulation, for different choices of radii like r or r tilde, these polyhedral metrics are discrete conformal. So the theorem can be stated in terms of conformal geometry as the statement that within a conformal class, the curvature determines the metric up to scaling. That's what the theorem says. So, let's talk about discrete uniformization theorem for circle packing. Just like in the smooth case, you only need to prove the uniformization theorem for simply connected surface, and so if you assume the surface is simply connected, and you prove the uniformization theorem for simply connected surface, and then you prove a uniqueness statement, which is true in the classical case, and then that implies the uniformization for all surfaces without any constraint on the topology. So you apply to the surface, which is a torus with a Cantor set removed, and you have the statement. And similar things happens here. And so let's just first focus on the simply connected case. And both Schramm and Herr prove the uniqueness theorems. And so there is a discrete uniformization theorem in the circle packing for all triangulated surfaces with no constraint on topologies, compact, non-compact, infinite topology. So let's consider the simply connected. So there are three of them essentially, right? In the classical case, we have in the conformal geometry, a simply connected Riemann surface. There are three types: the two-sphere, the complex plane, and the disk. And there are also these three classes here as well. So let's first focus on the two-sphere, which is a compact, and it's in some senses relatively easier. And also, if you have a circle packing with a two-sphere, so I'm going to state in a version which is not really a two-sphere. And so suppose you have a two-sphere with a spherical metric, and you have a circle packing of it by round spherical disks. You can always remove one round disk, and that becomes conformally a disk. And so I'm going to state the theorem in terms of the disk, which is more applicable in some senses. So here is the two-sphere case. Usually is called a curve Andreev Thurston theorem, which I'm going to tell you. It has also many. This can also be considered as a discrete Riemann mapping theorem. So before stating it, let me introduce a few wording. So suppose P, script P, is a collection of interior disjoint round disks. In the complex plane. So it's a picture will be something like this. Maybe something like that as well. And then you can introduce the nerve or combinatorics of it. Then it's nerve. I'm going to denote by NERP is a graph. So this is just to try to extract the combinatorics of it, which is more or less the triangulation you can extract at the beginning. So it is a graph. And so its vertices are the centers VI of DI. So here you have like D1, and then I produce the first vertex. So for every disk, I produce a vertex, say, associated to the center, and the edges are parallel vertices where DI is tangent to dj. So, so in this case, we have this, this graph. So that's a graph. And so if you have a circle packing metric where the curvature is equal to 0 above, and then the graph, the nerve of that circle packing in the plane is just the one skeleton of the triangulation. And so here is the discrete version. Usually they consider the discrete Riemann mapping. One can also think of that as a discrete version of the uniformization theorem on the two-sphere. Yes? Yes, that's a great question. And so for a circle packing, this is called a collection disjoint. This is allowed, okay? So suppose I have a collection of disjoint circles like that. The nerve is just the quadrilateral. That's allowed, okay? That's allowed in this definition. But the theorem will say, so I'm going to tell you the theorems. This will rule out. Okay. So here is a theorem. So let's take T be a simplicial triangulation. That's a necessary condition of the closed disk D bar. Okay. So this is a finite case. And so maybe later on, maybe on Friday, I will show you some pictures because it's going to take time to set up. So there are some really very beautiful pictures illustrating it. So for now, I'm going to just draw a hand drawing some pictures. And so here is a triangulated topological disk. So this is a purely combinatorics. And then the theorem says that then there exists, in fact, the unique up to Möbius transformation. That's uniqueness theorems of a collection of disks. And so, should I state this? Of a collection of disks inside the, so this P is just, I can produce a collection of interior disjoint around disks. Now, it lies in the interior of the open disk such that first, its nerve is given by this picture. So nerve of P is isomorphic to the one skeleton of the triangulation. So maybe I'm going to write, yeah, just like that. And that's easy. You can do a lot, things like that. And second, in this triangulation, there are some vertices which are the boundary of the disk. So these are the boundary vertices. And we require these boundary vertices correspond to the circles tangent to the unit circle. So V lies in P boundary vertex if and only if dV, this is the disk here associated to that is tangent to D. So in terms of the picture, I'll try my best now to draw it. So these two vertices now correspond to two circles lies in the interior of the unit disk. And the rest of it are now boundary guys. And so this will be This 3 will be the one tangent to the unit disk, and this will be the one tangent to Z. And then this is the one tangent to, this is no longer a circle. And there will be 2, right? And so, so there will be something here, and then there will be something here. Okay, so I hope you see the picture. That's the picture. And this pattern is unique after Möbius transformation. You can always apply Möbius transformation and make it. And so the nerve of this is exactly this picture. And of course, you can always apply Möbius transformation and make another circle packing, and that's the only way to do it. And the uniqueness of this part is essentially follows from Thurston's theorem above. And you can always, so far you may think that this is something about the disk which is not related to the uniformization of the two-sphere, but you can always add. And so this last condition really says there is one more disk which is a complement to the unit disk. And this is the circle packing of the two-sphere. You add this disk to it, and this disk corresponds to a point, a vertex, right? And so you will get a triangulation of the two-sphere. Yeah, this is really a triangulation of the two-sphere, and that's a discrete uniformization theorem for the two-sphere setting. So that's the story behind this theorem is also quite interesting. It was really, this statement is really was really proved by Kerb around 1929, and nobody paid attention to it, and so it was completely forgotten. And then Andreev was working on the convex polytopes of angle at most pi in hyperbolic space. He proved existence in uniqueness theorems, which covers this case. And so he allowed really these circles to be intersect with intersecting angle at most pi over 2. He gave a complete characterization without, he also didn't notice that. And Thurston was working on geometrization of 3-manifold and introduced a circle packing metrics, and his method also gives a new proof. And Thurston didn't know Kerb as well. But nowadays we call this, this is the famous KAT theorem. Okay. I'm going to tell you one application of it. And yeah. No, under some normalizations, just reduce it. You see, I try to avoid spherical in this setting, right? Yeah. This is Euclidean, but if I just apply a little trick of the normalization follows from that. So the proof, that proof appears in modern Rodden's paper. Okay, before I tell you why we should also consider this theorem as a discrete Riemann mapping theorem, I'd like to tell you this work by Her and Schramm for the non-compact case. And so I like to show you really the whole picture of discrete uniformization in circle packing for all surfaces. And then I'm going to come back to this theorem and say why this is also a discrete Riemann mapping theorem. And I also tell you why this picture really gives an approximation to Riemann mapping as well. So this is a pi 1. Suppose the surface is not simply connected as non-compact. It's, by the way, it's much more difficult in this setting. So suppose I have a non-compact simply connected surface. Basically, topologically is a complex plane, and I have a triangulation. It's an infinite triangulation of it. What can you say about it? So here is a theorem by, well, first it's a Schramm, and then John Hay. This is more or less Schramm's PhD thesis, and then this is a little bit later. The statement is really striking as proof is, I'm going to tell you on Friday the proof of Her. on this case is a really beautiful idea using discrete Schwartz lemmas. And so, but I'm going to tell you the statement first. So here is a statement. So let's let T be again a simplicial triangulation. It's a topological triangulation of the complex planes. This is the infinite triangulation. So the simplest one is of course the regular hexagonal triangulation of the plane where the degree of every vertex is 6. So, then the statement is that then there exists, in fact, is also unique up to Möbius transformation. The following two cases. A collection of circle disks. So this is a circle packing D in the complex plane. This is the infinite collection of circle packing round disks with disjoint interior whose nerve E is isomorphic to the one skeleton of the triangulation. So I'm going to call the one skeleton of the triangulation. Let's call it FO1. Okay. And this is also unique. So the uniqueness was, in fact, first conjectured by Thurston for this infinite regular hexagonal triangulation. We know for this guy, you can produce a circle packing where all circles have the same radii, and then the underlying combinatoric is regular triangulation. And then Thurston's conjecture, which I'm also going to tell you the Thurston conjecture relating to the Riemann mapping. But the first conjecture is that whenever you have a collection of interior disjoint round disks in a plane, which are locally finite, which is also needed, and so locally finite. Meaning any compact set intersect only finite number of disks. And so you don't want to have these circles accumulate in a finite stage to something, and then the packing is not clear. So there is a locally finite circle packing of the plane, whose nerve is that. And so Thurston conjecture that you have a locally finite collection of circles in a plane where every circle is tangent to exactly 6 others, and the complement of that are these triangles. And that's a triangulation condition. And if that happens, all circles have the same radii, and that was proved by Schramm in 1990s. And the argument is really amazing. It's purely topological degree counting. And the second part is this or. So this is a uniformization for the simply connect the space biholomorphic to C, or there is a circle packing in the open disk whose nerve is equal to Z. So that's what John had proved. And so you have the uniqueness and existence of theorems. And whenever you have a uniqueness, then that implies this theorem is true for any triangulated surface. And so this is a uniformization theorem. So for any triangulated surface S, V, T. And this theorem is really general. I do not even assume this triangulation to be simplicial. The only assumption which is necessary on this triangulation is that if you look at the universal cover, there is a universal cover surface of that. You can pull back the triangulation to the universal cover. The triangulation in the universal cover is simplicial. That's a necessary condition. Okay, so So I'm not going to say more about it, but let me just say, for any triangulated surface like that, then there exists, in fact, a unique complete metric, complete Riemannian metric. Of constant curvature, zero, minus one, one, and the circle packing on this surface. Now, with the Riemannian metric, we can talk about what is the meaning of a circle, round circles, and tangency, whose nerve is isomorphic to one skeleton. Okay, so that's the ultimate theorem in circle packing. It's a really striking theorem that you assume no condition. So you give me a torus with a Cantor set removed, you produce a reasonable triangulation with this condition. Then you can find a complete Riemannian metric. If you take a torus with a Cantor set removed, then the Riemannian metric will be -1, and you can produce a circle packing in this metric. And this circle packing is also unique up to Möbius transformation. There is some scalings because of this. So that's a discrete uniformization theorem. The theorem for it's like in a classical uniformization case, when the surface is compact or closed, it was first proved in Thurston's notes. And so Thurston proved the uniqueness using this sort of finite variation, finite observation. But the proof for the infinite rigidity is much more difficult. And then for the infinite non-compact case, it was really this. Okay, so that's the uniformization theorem. And now I like to, before I go to the next, I'd like to tell you a little bit about the convergence. And so why is this a good approximation to the smooth case? And how is this discretization related to the conformal geometry in classical case? And so this is the Thurston's conjecture. On convergence. No, when we talk about circle packing, you need a metric. It's a round disk, and round in what metric, right? So this circle packing, I really means this is a collection of round disks. So there is this collection, a potentially countable collection of round disks in this surface of constant curvature, just like here. I mean, we are using really Euclidean metric, and whose contact information, this contact information, is exactly given by your triangulation. Yes, the number of circles are exactly indexed by V, and two of them are tangent even and only if there is edge between the two. So that's a theorem. Yes. Yes, yes. Okay, maybe I should state it in that. So the theorem can be say you can find R from V to R. So you asked a really good question. I skipped some of the, sort of suppress a little bit. So if we go back to the original definition, the theorem says, I give you this, I can find a radius to here. And now there are three choices, either hyperbolic or Euclidean or spherical. Okay, so that, let me assume we know the underlying metric is Euclidean. Then the theorem says I can find a metric here such that the curvature is equal to 0 everywhere, and the metric is complete. You may not be able to, even the curvature equal to 0, it may not be complete because of non-compactness. And that metric is unique. There is also a possibility that the final prediction is hyperbolic. That will say there is unique such H where instead of using Euclidean triangle, I use hyperbolic triangle to glue them. I make this condition valid, the metric is complete, and this is unique. The same thing for spherical. So that's what this is. No, it's a complete hyperbolic metric. A complete metric of constant curvature. It's exactly the same as what happened in the classical uniformization theorem. Okay, so Thurston's conjecture on convergence is another really amazing conjecture and was proved by Rodden and Sullivan theorem. So I will be, because I'm running out of time, I just want to tell you what the theorem is. This is a very beautiful theorem, and it's related to the sphere case. So the theorem is this: you take omega to be a bounded, simply connected domain in the complex plane, like this. And now we know, say you take a point. Now we know there is a Riemann mapping. So F is a Riemann mapping. Sending this omega to the unit disk. And normalize it. And what Thurston says that these discrete circle packing construction gives you a very nice approximation to the Riemann mapping. And so that's another justification that this is a good approximation scheme. So here is his construction. You take an integer really big, and now we start packing the plane by the equilateral triangles. Like this. So you look at the set of all circles, so these are radii 1 over n, fix n, and look at the set of all circles lies inside your domain, and that will produce an approximation to this domain. So look at the nerve of it. This is now a geometric nerve. Okay, and which has admits a triangulation because of the circle packing. And so we get, what we get is now a approximating domain, which may assume simply connected, together with the triangulation. So this triangulation are these blue triangulations coming from the combinatorics of this regular hexagonal circle packing. Now, if you apply AAT to this circle packing, so this is by, at any rate, you have some kind of a triangulation, simplicial triangulation of the topological disk. And so you get a circle. You get a circle packing of it, whose nerve is the same. And let's do a normalization. So there is a point P containing close to some vertex, and then you look at this vertex sending to that to 0. Okay, so there is this approximation. This is the map. At the moment, the map is only defined as the vertices. So you know this vertex is going to send to the center of the corresponding circles because they have the same combinatorics, and then you extend it piecewise linearly. So this is a linear extension. On all triangles. So you have a piecewise linear homeomorphism from this polygonal approximation to the disk, and the conjecture is this is convergent. So the conjectural system is that this is, in fact, uniformly convergent to the Riemann mapping, and the theorem says, the answer is yes. And that tells you that these sort of the finite stage approximation is indeed a good approximation to the Riemann mappings. There are now many softwares where you can apply it, and so using the software you can really see what happened to the Riemann mapping. So you will see where this point goes under the Riemann mappings using these softwares. And it turns out it's very interesting that suppose your domain is a Jordan curve, say smooth Jordan curve, and these curvatures here really gives you a lot of effect on the accumulations of the circles. And so I will show you some pictures on Friday. So okay, so that's the whole picture. I'm sorry, I'm a little bit slow. Oh, okay, so maybe I can take 5 more minutes. Okay, so that's the story of circle packing. As I mentioned, I will, on Friday, give you a proof of the uniqueness part here. This is the proof by John P. Using a discrete Schwartz lemma. Okay. A really beautiful Schwartz lemma. First proved by Bearden and Stephenson. It's really the analog of the classical case. You go back to the proof of the uniqueness part of the uniformization. The uniqueness part here, which says that suppose you have two hyperbolic metric on the open disk, which are complete and conformal, then they are the same. And the proof is the Schwartz lemma. So these approaches really try to discretize those ideas, and there is indeed, in this case, a discrete Schwartz lemma, which I'm going to tell you. And the proof from Schwartz lemma to the uniqueness is extremely beautiful and short. So I will tell you on Friday. It's just a picture, you will see it. Okay, so now let me tell you the second story, which I will continue on tomorrow. But this is sort of a warm-up of this picture. This is, oh, I should tell you the variational principle. Yes, sorry about that. Let me tell you the variational principle proof of this. So you will see the Schlafly, essentially the discrete Einstein-Hilbert functionals really plays a role here. So there are several of them now, but let me just tell you one. So we know there's a relation, one of the main problems in geometry is to study the relation between metric and curvature. In our setting, which is really simple and elementary, it's really the length of the triangle, that's a discrete metric, and versus these angles. So that's a cosine law. In the Euclidean setting, so I'm going to use just write this down for reference. You all know this really well. And there is a similar one for spherical and hyperbolic cosine laws. So here is a very interesting observation by my collaborator Chow and myself. It's just to put it into a little bit more interesting context, and this is very useful for computations, and so I like to single this out. In fact, this is true for all Euclidean spherical or hyperbolic triangles of lengths and angles like that. we have these two statements, which is, it turns out we know the cosine law takes different forms for spherical and hyperbolic and Euclidean, but when you take derivative, they all have the same form. So the first formula is this: partial theta I partial Lj is equal to minus partial theta I partial Li cosine theta k. So these indices are distinct. Okay, so this is true for all triangles in constant curvature metrics. Ij, k's are distinct. And 2, partial theta I partial Li is equal to, is always positive. And that's sort of the standard observation from Euclidean geometry, right? If you fix these two lenses and you increase that length, and then this angle is going to be increasing. But you can even quantify this as 1 over, let's see, I'm going to use this, Lj sine theta k. This formula, if I write it like that, does not hold for spherical or hyperbolic, but it's not very far. So if you want a formula which is valid for all cases, it's really this phi of Li. You just modify the length a little bit, where this phi of t, just this length respects the curvature. So is equal to t in the Euclidean case, sine t in the spherical case, and sinh t in the hyperbolic case. Okay, so it's really the curvature which plays it. And this formula here, I and j, you can interchange it, and that's because of the sine law. Okay, so you can interchange I and j, that's a sine law. So that's a formula for all cases. And the second, if you put it in this form, that will be true. So let me now state, I'm going to tell you what Dividier's formulation of substance, sort of soup version of it, and you see the variational principle, and I'll stop. And again, his theorem is true for all hyperbolic, spherical, and Euclidean. But let me just make it simple for the Euclidean. So for a Euclidean triangle, Lk with angle theta as we with Li equals Rj plus Rk. And so this is his variational principle for circle packing. These R and J's are the radii, and here is his main observation, which is highly non-trivial, and at least to me. So let's write Ui. You make a change of variable, log I. So instead of taking the standard length, you take log of it. Then you have the two following statements. The first statement is a partial theta I partial Uj is partial theta j partial Ui. So Ij are distinct as before. And furthermore, this is a positive. The positivity is exactly what Thurston observed. That's this picture. That's this picture. And but these two are equal. That's the variation principle that he discovered. And second, if you compute Us, you look at the Jacobian matrix. This is really a matrix relating curvature and metric. This we now see it's a symmetric. But if you look at the sum of the rows, right? So theta 1 partial U1 plus theta 2 partial U1 plus theta 3 partial U1. This is equal to 0 because the sum of the angle is equal to pi. It's a constant. So this matrix is a negative diagonally dominated. So let me put this is a diagonally. Okay, and if you have something like that, you see, you can do a lot of very interesting things. So, so the first part will say the differential form theta I dui is a closed one form. And so I can integrate it. And the integration is the function u, f of u. So we can get a function depends on the radii. This is a variation of principle. And what does this says is that the Hessian of this function is this matrix. And so it's a concave function. R3. And what is the meaning of this? It says the partial f of partial ui equals theta I. And that's a Schlafly. Okay, so I will stop here, and I will tell you, this is now just a one-line proof. With this, you can prove Thurston theorems just by a simple variation of principle, and then I'll tell you the other versions. Okay. Thank you.